yeah, so here I'm Sunjing here, General Chair of EPSAC 2020. Sorry that we have to do this online, but then I'm pretty sure all of these the different chairs, PC committee, etc. have done a lot of work, and then I have received so many emails, which did show they have a lot has been done. All right, so let me get into this first technical session of the conference. We will be basically having our first keynote speak, which is given by Professor, well, we always call him Abhik. So Abhik is a professor, provost chair, professor of computer science at the School of Computing, National University of Singapore. And he's the director of a National Satellite of Excellence in Trustworthy Software System. He's also the PI of the Singapore Cybersecurity Consortium, right? Abhik does a lot of research in different areas with a focus on software testing, analysis, software security, trustworthy software constructions. And then he's also well known for his work on all kinds of really sophisticated techniques for program repair, right? And then he has a huge ton of papers which are published at the really top conferences, and also a number of good tools such as AFL Fast, etc., which has made a lot of impact, right? Well, he has been an associate editor of IEEE Transaction on Software Engineering, an associate editor of IEEE Transaction on Dependable and Secure Computing, Tolson as well, all of these top journals. To add on to all of that, I have to say that I was once his student taking his class 20 years ago, and to this day, I still remember vividly how well his class was, well organized, very interesting. So I'm always excited to hear Abhik talk. Let's welcome Abhik. Abhik, you want to share your screen, and then, yeah.
Sure. Thank you so much. Can you see the screen?
Yes.
Let me. Okay. Thank you very much, June, for this very kind introduction. You were indeed very kind with your words. And also thanks to all the organizers for this opportunity to present the work on automated program repair. So this is an area, of course, we are trying to kind of push the boundary of the technology because there are a number of applications probably which could benefit from. So this is also a very good opportunity to get feedback from all of the participants here. So it is indeed my great pleasure and great honor to present this talk on automated program repair. My name is Abhik Roychoudhury, and I'm from the National University of Singapore. Okay, so let's begin. Let's begin with this hypothetical. Of course, it's a hypothetical. I'm not unwell today. I'm here giving this talk. But suppose I was unwell today. So which one would be more manageable? Should I go to a doctor? Or if it is a small thing, like maybe I take a little bit of Panadol. Well, in Singapore, we call it Panadol. If you are from the US, you might have Tylenol. So should I take one of the medicines, and that would make me well? So of course, if it is a small matter and I can sort of self-diagnose and I can correct myself, heal myself, that would be more manageable. So what we are trying to do at a very high level, or at a very rather intuitive level, is for the program to correct itself, at least for the quote unquote small errors. But of course, this term of small error, this is a little bit work in process to clarify what kind of errors can really be repaired. So this kind of work is really beyond error detection. Prior to the work on program repair, we spent a lot of time, actually, even in my group in NUS, we spent many years working on program debugging. And one of the things we realized as a difficulty in program debugging, which motivated us to look into repair, is that it is very difficult to pinpoint exactly where the fault is. And not only that, it is often impossible to say that the fault is exactly at that line, because where the fault is, that depends on how it is fixed. It's really how I'm fixing it that really determines that what I call as the fault. In other words, where the fault is, this is often in the programmer's mind. And since we don't have a way of mind reading, it might be more manageable to fix the fault. So take this analogy. Suppose I'm sick today, and exactly where my sickness is, finding that might be very, very difficult. But as long as I can deliver this talk, I can answer your question, I can clarify all the doubts about automated program repair, then I have done my job, right? So this was really the intuition. It's really a true, description of events. This was really the intuition with which we started working on automated program repair. That where the fault is, not only it is difficult, but often it might be impossible, because what the fault is, that depends on how it is fixed. So therefore, why don't we work on the fixing itself, rather than trying to find out what's wrong with the program. So as a software engineering process, or for that matter, a program analysis technique, I prefer to call it as a specification inference. And this is also quite interesting to me from my personal perspective, because before working on all of these things like testing, debugging, repair, for my own PhD, I had worked on formal methods, in fact, quite heavy formal methods on theorem proving and combination of theorem proving and model checking. So one of the difficulties we sometimes face in formal methods is that the formal specification may not be available, as a result of which applying the formal method is difficult. So this was also of interest to us in those times when we started this work, that this is also one way of circumventing that, even if as a little step, that we can infer specifications about the program behavior. So in other words, we are trying to answer the question, what would make this program correct, and trying to get a formal specification of that. So these were roughly the two intuitions with which we started this sequence of works on automated program repair. One is that what the fault is, oftentimes it depends on how it is fixed. So why don't we look into fixing? And the second is that this allows us to infer intended program behavior. Oftentimes, if the formal specification is not available, this allows us to infer intended program behavior through symbolic execution, through a technique that we use called symbolic execution. There are some other subsidiary intuitions which I will try to get to towards the end of the talk. Okay, so why should we look into automated program repair? Of course, whenever we try to develop some frameworks, some techniques, some tools, there should be applications. So one of the applications, which is the most popular, is of course maintaining legacy software. This is very, very important. Debugging aid, of course, if you have the bug pinpointed either through manual or automated means, often manually, then this is a way of fixing it. So this is in fact a use case people are already studying, that when you actually push a commit, if tests are failing, whether actually it can come back with some suggested fixes when you try to put in a commit into a system. Then in education, this is actually an area which is becoming very, very important. If you are an academic staff in computer science anywhere in the world, we would know that the enrollments are going up. So the teaching of programming, there are lots and lots of students. So we are looking at things like automated grading and automated feedback generation. But this is a direction which is very big, and this is very much work in progress. There is a lot to be done there. Security patches, this area is more immediate. People have started looking into it. We have also looked into it. And there are other groups which are looking into it. This is to reduce the exposure to vulnerabilities. I'll talk a little bit of that. And finally, also in self-healing systems. So for example, drones, because in future it is envisioned that there will be aerial mobility using probably drones. And what if the drones are probably compromised, or they face some errors or adverse conditions, whether they can correct themselves and continue on their journey. The application of drones are numerous, like disaster recovery or going into areas where the human beings wouldn't want to go into, for example, due to COVID and so on. Okay. So, well, of course, we could go on and on and on the applications, but these are some of the application. And broadly speaking, they could be divided into these three categories: productivity, education, and security. So, of course, one could choose their own area, which one they are more interested in, and also focus customize this line of research and focus more. And there is quite a lot of opportunity. I really feel there is quite a lot of opportunity in this area. So let me proceed now with the techniques. So this is one of the old or one of the conventional ways, I would say, in which we could do automated program repair, or this is one of the intuitive ways we could start with. Suppose I have a program. So this input is a buggy program which passes most of the tests, but fails one test. Then you generate several mutations of the program, and you try to see whether they are fit. Okay, so you could evaluate their fitness by checking how many of the tests they pass. And if some of them pass all the tests, then you accept it. Otherwise, you reject these mutations. So this way of doing the program repair only by search, this would be very intuitive. It would be very flexible because you can make any kind of mutation. This is in fact one of the benefits of this approach. It would be very flexible. So you can do arbitrary insertion, deletion, anything. You can change the program in any possible way. But at the same time, there are lots of issues. Of course, the program can be very large, but even more than that, there could be a very large search space. And for automated program repair, the scalability in terms of the search space is more important than the scalability in terms of the program size. So there would be a lot of mutations to consider. And then what would be a good way to decide what would be the best? Plus, there is this additional problem, which is sort of the key technical challenge to solve in automated program repair. And a lot of colleagues all over the world are working on it. Including us in Singapore, that is overfitting. And I'll spend a bit of time in this presentation on this topic. So let's move on. So roughly speaking, in automated program repair, whenever we describe a process, a software engineering process, we have to describe what are the inputs and what are the outputs. So the inputs are the buggy program and some tests, because we are assuming that a fully formal specification is not available. So what can we do? Even if a fully formal specification is not available, what can we do to generate a poor man's formal specification, partial formal specification from there, which we call as the specification inference. And we are actually trying to modify a flow like this, where we have a buggy program and we have tests, and we generate many candidate patches by these so-called transformation schemas. So these are the mutations that I mentioned earlier. We generate many candidate patches, and from there, we try to choose some of the candidate patches, the ones which at least pass all the test cases. But just choosing the patches which pass all the test cases is insufficient, simply because if your tests are in the form of input-output examples, say input 1, output 1, input 2, output 2, and so on, there is nothing preventing you from converting the program into another program which just says if input 1, return output 1, if input 2, return output 2, and so on, right? So if I just have, this is almost like I just have to pass these test cases and that's all. So if I just keep this criteria, this is very, very weak. I can come up with this really unusable or nonsensical programs like this: if input 1, return output 1, if input 2, return output 2, and so on. So this clearly, from an understanding point of view, this is quite clear that this will not serve our purpose. So there should be some quality indicator of the patches that we generate, or of the code that we automatically generate. There should be some quality indicator which prevents this kind of code from creeping in. We wouldn't want that. And this is where, this was again the intuition with which we try to work. This is where the symbolic execution can come in. That because the symbolic execution can synthesize or help you synthesize certain specifications, which can then help you synthesize the automatically generated code to fix the program. Okay, so let us now try to describe. So these are all some of the intuitions. Let us now try to describe some of the intuitions through an example. So at this point of time, we have not looked into any technique. So we have only given out the intuitions. And now maybe we go through an example to cement those intuitions, and then we can briefly discuss some of the techniques. So this is an example that all of us would be familiar with. All of us here are researchers, so we have all cleared middle school and high school. We know what is a equilateral triangle, isosceles triangle, and scalene triangle. So an isosceles triangle is one where two of the three sides are equal. So clearly this code is wrong. It should have said that if A equal to B or B equal to C or A equal to C, where A, B, and C are the sides of the triangle. Okay. And then here I have a test suite. It's not a contrived test suite. It is exactly the kind of tests that somebody would write. There is one test for an invalid triangle. There is one test for an equilateral triangle. There are three tests for isosceles triangle. This would be the usual way we would write the test because two of the three sides are equal. So which two? And there is one test for a scalene triangle. So this is the usual kind of test suite. Given our experience in testing, for any of us, this is the usual kind of test suite we would probably write, not very far from it. And then there are some tests that are passing and some tests that are failing. So now if we look at the search-based approach, what do we need to do for solving this problem of the isosceles triangle? What we need to do is we have to look into all sorts of mutations of this program. Okay. Of course, as we said, that there are often many places in the program where the program has to be fixed. Even if I got a dream yesterday night that I have to fix line number 6, that means I know this somehow. Even then, it has to consider all possible mutations of this line number 6. And as it turns out, actually, this the search-based approach for almost all implementations, if not all implementations, will find it very hard to generate the fix for this very simple program. Simply because, and the intuition is very simple, simply because the search-based approach is trying to copy the fix from somewhere else in the program. Okay, so we can think of it as something like skin grafting. Suppose I go to play a contact sport like football and I lose some skin in my feet while trying to dribble, and then I try to copy some skin maybe from my hand and try to put it in my feet and try to see if it works. So the search-based approach is trying something like this. It's trying to copy code or sub-expressions or portions of code fragments from elsewhere, and trying to put it into the designated fixed location. Of course, the code could be from the current program or previous versions and so on. So in this case, this expression does not appear anywhere else in the program, and as a result of which, the search-based approach is going to have difficulty. In the semantic approach, which we have not described yet, but we can still think of it intuitively. In the semantic approach, if I know that I have to fix line number 6, what I can do is I can say that here I have an unknown function of A, B, and C. So A, B, and C are the variables of interest. In general, we can consider all live variables at that point. So we can have an unknown function in A, B, and C and try to synthesize properties of that function. And this is what we mean by specification inference. So we have an unknown function f of A, B, and C, and we try to synthesize properties of that function. Okay, so specifications of that function, of what that function should be. So it's a very small step specification inference, not specification of the entire program. Excuse me, not specification of the entire program, but rather what this line should be. So for this particular line, so f of A, B, and C, from the test cases, so as it turns out, 4 of the 6 test cases will reach this line. So for the test cases, we will get exactly a property like this, that for 2, 2, and 3, it should return true. For 2, 3, and 2, it should return true. 3, 2, and 2, it should return true. and 2, 3, and 4, it should return false. And from there, when this is fed into an existing program synthesis engine, so I'll talk a little bit of that later, it would automatically generate fixes like this, that is either A equal to B or B equal to C or A equal to C, which as it is exactly the fix that we needed. Okay. So this is more or less the intuition behind the works that we have done on automated program repair. Of course, the way it was illustrated here, there is a significant role to be played by the program synthesis engine in the backend. In summary, as comparing this approach, this semantics-based approach or the symbolic approach to the search-based approach, both of them are trying to divide this automated repair software engineering process into 3 parts. In the case of the search-based or the syntax-based approach, the 3 parts are, the 3 sub-processes are where to fix, that means which line to fix, generate patches in that line, and then validate those patches by running the tests. The tests are your correctness criteria that is available. In the case of the symbolic approach, you still have where to fix, but then the second thing is, once you decide which line to fix, you try to ask the question, what values should be returned by those lines for the different tests that you have? Okay, and then you try to generate expressions which meet those values, which produce those values. Okay, so this is exactly what we mean by specification inference, because it is trying to ask the question, what would make the program correct? What value should I have returned here, at least for these tests, which would make the program correct, which would make the test pass? Okay, so now getting a little bit into the technical details, the way we can accomplish this is through a technique called symbolic execution, which I will describe in a minute. So given a test input, we execute that test input up to the line where we want to generate the fix. And then wherever we want to generate the fix, we call it as an unknown function of the live variables. Okay, and then if this unknown function is a symbolic variable x, okay, an unknown x, then we try to generate properties of x by traversing the various paths from this line onwards and try to see what property should hold for x for us to rescue the execution of this particular test input. So now, in terms of symbolic formula, I have to give you some of the symbolic formula, even though it might look a little bit daunting, that this is really the path condition. So this is the disjunction over the paths, and this is a path condition. And then the expected output, that is the value that you expect for this test, that should be equal to the output expression. Okay, and then this is all a property on x, so this would all be a symbolic formula on x, and then you relate the unknown function to x. This x is not any x, but the function that we want to synthesize for this particular test input. This is the x that we have. Okay, so in this case, as in this example, as we showed, this was actually this is another one we are trying to describe. So this is an altitude control program, as I see. And suppose the error is in bias equal to downsep, and we have to replace it with bias equal to upsep plus 100. That is quite a bit of work. So we would not be typically getting it just by arbitrary mutations. So given this test and given this expression, we can try to see the technique in action. So the first step is debugging, that is trying to find out where exactly we should fix. And for debugging, we are actually using this statistical fault localization, but there could be other kinds of debugging techniques also that can be used. In fact, in later works, this one I'm presenting a very early work. In later works, we have used other kinds of debugging techniques. But let's assume for a minute that we have statistical fault localization for the purpose of debugging, where we assign scores to the different statements in the program, and the scores are assigned based on their appearance in the failing and the passing executions. So in this case, a score is being given to statement S based on how many failing executions S appears in and how many passing executions S appears in. So if a statement is almost always appearing in failing executions and never in passing executions, typically it would be given a higher score. And again, this is just one way of scoring. There could be many, many other ways of scoring. Suppose with this, we have actually identified line number 4. Then we replace this right-hand side with this unknown function on all of the live variables. So this unknown function on all of the live variables is this f. And as it turns out, the symbolic execution in this case will go through these two parts and will produce property like this, that given this input 111 and 110, it should generate an output which is greater than 110. Okay. So this was the intuition of how the inferencing is happening, but the inferencing at the back end is using a technique called symbolic execution. So we of course want this talk to be self-contained. So in case we are not familiar with symbolic execution, so I just have it as an inset in this talk. It's no worries. It's really a very, very simple technique. So in this case, suppose I'm showing symbolic execution for the purpose of unit testing. So I have this program or procedure called test me, and it takes in these inputs, climb and up. So you really try to consider these inputs for the purpose of our testing. The inputs here are climb and up. You really try to consider these inputs as unknown, okay, or symbolic. So for our purposes, let's call it unknown. And then as you kind of get any condition on an unknown, you just consider both possibilities of that condition. So since climb is unknown, you would consider climb greater than 0 is true or climb greater than 0 is false. And similarly, if sep is unknown because sep is dependent on up and up is unknown, then again you will consider both of those possibilities. But note that all of the decisions are really on the inputs, are converted into decisions on the inputs, because all of the program variables could always be described as expressions in terms of the inputs. So in this way, you could construct a symbolic execution tree like this. And essentially, through symbolic execution for our purposes, we could try to find out that what are the paths which would rescue the execution. Okay. So with that, just to conclude this part of the talk, with that, I would get a small property like this for this one single test case. Of course, this is not enough for me to constrain the space of fixes. I want to get enough of such properties so that I can constrain the space of fixes and I get a nice fix. Okay, but then note that from each test, you can get one such property which would constrain the space of fixes. And furthermore, you do not even need to use program synthesis in the back end. If you have a space of expressions, okay, if you have a space of expressions which is described maybe nicely by a grammar or some other suitable formalism, you could search over the space of expressions while respecting the axioms of the operators that appear in those expressions. So like, for example, plus is commutative, x plus 0 is x, and so on, so that you don't generate redundant expressions. You could search in those space of expressions, and you could put that as the backend instead of program synthesis. So really speaking, what we are trying to present here is not exactly what the backend is. The backend could be a search like this. The backend could be program synthesis. The backend can also be second order constraint solving, as I will show in a minute. There would be several choices of the backend. But the front end is the symbolic analysis, which comes up with the constraint that the backend has to satisfy. It's providing the constraint on the space of fixes. And this is really the contribution, so to say, we are seeking to make so that the repair becomes a reality. Okay. As I mentioned, the whole process of program repair could always be seen as a second order inferencing as opposed to a first order inferencing. So now getting a little bit more formal, if I may, we can directly solve, as we said, that if we know this is the line we want to fix, and this is an unknown function, and then we call this unknown function is x, and then get symbolic formula on x, we could directly solve this unknown function by building a second order symbolic execution engine. So actually, if we think about it from a formal point of view, the program repair problem, where we are trying to generate expressions at suitable lines in the program, when looked at it directly, it's really a second order inferencing problem. So it is possible. In the early works, we did not do it that way because we did not have all of the capabilities for building a second order engine. But later on, some years back, we also looked into building a second order symbolic execution engine directly, where we try to allow for these existentially quantified, only existentially quantified second order variables, and restrict the interpretation to a particular language. So for example, the space of expressions could be given by a grammar like this, and this is, say, representing linear integer arithmetic. Okay. This also has other advantages. I will not get into the details of that for interest of time, but this also has other advantages because depending on the space of expressions, you can find out additional kinds of infeasibility. For example, if the space of expressions only allows for monotonic functions, so therefore you cannot have in constraints like this, that row of 0 is greater than 0 and row of 1 is less than equal to 0. So such kind of constraints can be called as infeasible or unsatisfiable when you are doing this kind of second order reasoning, which we also do because the second order reasoning itself has a significant overhead. So therefore, to compensate for that overhead, you can try to do these kinds of additional sources of infeasibility or unsatisfiability so that you can make the second order reasoning very, very efficient. I'll not discuss the details of the second order reasoning, but just a little bit of intuition. So the way we would represent these, this is the encoding that we found quite useful for representing the space of expressions. So this is, for example, a tree, an expression tree, where each node has these selector variables, and only one of these selector variables will be true. So if this selector variable is true, then it represents the expression x. If this selector variable s13 is true, it represents y, minus, and so on. So depending on the choice of the selector variables, whether they are true or false, that would make this tree represent one particular expression, and such an encoding can represent a host of expressions. So this is the way we are actually representing sets of expressions for as the backend for the second order reasoning, second order symbolic reasoning. And in terms of efficiency, what we found out, so here are some of the experiments on core utils. I would really not get into experiments within the talk because that would be probably too fine-grained. But in terms of efficiency, we found that the second order reasoning is quite agnostic to the number of paths, and this is not unexpected number of paths, but the general overhead itself is quite high. Okay. So now wrapping up this part of the talk, I understand I probably have 15 more minutes or so. So now wrapping up this part of the talk. So essentially we are trying to combat the overfitting problem that we mentioned by doing symbolic inferencing, at least on the input-output examples that you have. We are trying to do that. And this already makes the technique less overfitting. There's still overfitting for sure, but it makes it less overfitting than the search-based approach, as we observed even in very initial experiments that we did many, many years ago. And that's partly because essentially, if you have already considered a test which goes through a certain path, if you have other tests going down the same path, this technique based on symbolic reasoning is unlikely to overfit those tests. This is, again, the intuition. So then now, given this kind of a semantic inferencing, or rather specification inferencing engine, where we looked into a flow like this, we have tests, then debugging, then dynamic symbolic execution, followed by synthesis or other kinds of backends. You can look into various variations of this. For example, we can try to ask the question that instead of thinking the program as a piece of software, why not think of it for a moment, just for a moment, let your imagination run wild and think of it as a hardware circuit. So if you think of the program just as a hardware circuit, and then you can ask the question, what is the minimal change in wiring that would make the program correct, at least in terms of the observable outputs of the hardware circuit. We always have such questions in hardware circuit. So why not try to bring the same intuition into the program? You can now try to ask the question, given these tests, what is the minimal change for some definition of minimal, say the minimal syntactic change, which would make the program pass all tests. And then this becomes a technique which can be solved by a max SMT solver. So not just an SMT solver, but a max SMT solver, but presumably will not be very scalable. But this gives us some ideas. Instead of trying to directly solve the entire repair process by a single call to a max SMT solver, which probably may not be very wise, we can try to ask the question that instead of getting these specifications in terms of constraints, can we extract suitable values? Of course, values are much more manageable than constraints. Can we extract suitable values, but without constraining the space of fixes too much? Because if we constrain it too much, then again, we will be back to square one and we will be having the overfitting problem. So this led us to one piece of work that we did called Angelix, where given a failing test, which can probably go through many, many locations where we could insert fixes, we try to ask the question, if I drove the failing test through this path, say on the leftmost path, what are the values I can give for these expressions E1, E2, E3 that I need to put in? Okay, so what values would rescue this execution? If I go through this other path, what values would rescue the execution? Maybe certain paths are not even feasible. So instead of trying to capture, so this is a very subtle change and this is a little bit technical, but instead of trying to capture the space of fixes through constraints, you try to answer the question that if I drove this particular test along this path, what values would make me rescue the execution? And of course, that reasoning is much more efficient. So we call these angelic values because, of course, they would allow us to rescue the execution. So to sum up, so there are a number of works that could be done, and I'm sure there could be other ways of doing specification inferencing, and this would be very, very nice because I think there is a fairly large area to be explored. These are some of the works that we did where we inferred every time a different kind of specifications. This is just, this is an initial work where we try to get specifications on a single line fix that we try to generate. The later one through max SMT, where I mentioned the whole program is a repair constraint. And then the value-based specification, where we still retain the flexibility of the program going through different control flows for a particular test. Okay. So this is probably getting a bit too detailed at this point. So let me step back and try to take a broader picture. So this kind of techniques can be used for the purpose of, for example, security vulnerability repair. And I'll talk in more details about that. Plus, it can also be used for vanilla program repair at a fairly large scale. As I mentioned, the scalability, just the way the problem has been framed, it would be clear that the scalability with respect to the program size is not so critical, but the scalability with respect to the search space is very, very critical. So these, even in the earlier incarnations, these were run on this kind of symbolic inferencing because we are containing the search space and we are keeping the number of symbolic variables low, were run on fairly large programs. And also, this is just as maybe as a trivia, just to pick our interest today morning. This is a fix that is generated automatically for the Heartbleed example, which we are familiar with, which is functionally equivalent to the developer-provided repair. But we did look into the security vulnerability repair more extensively, so I will talk about that. Okay. So now these were the search-based and the semantic approaches. In the interest of time, I will not discuss the other approaches too much, but it is possible to take some middle path or in-between approaches. So, so we are here in the Asia Pacific Software Engineering Conference. So this middle path or middle way, this is actually an Asian philosophy. which in Chinese it's called Zhongdao, and in Sanskrit this is called as Madhyama Pratipada. So this means that the life should be led in moderation, neither in luxury nor in austerity. So maybe I don't know whether the search-based approach we call as luxury or austerity, or the semantic approach we call as luxury or austerity, but we can take in-between approaches where instead of the search-based approach working on individual fixes, it works on equivalence classes of fixes. And these equivalence classes excuse me, the equivalence classes could be defined based on various semantic artifacts, like, for example, values observed on tests or on program dependencies and so on. So this is something we have looked into as well. But in the interest of time, I will not get into the details of this. But in fact, this approach leads to very, very efficient. If you care about efficiency, this approach leads to very, very efficient repair. Okay, and you can actually see some of the results over here. Okay. Given this, there are also other ways of improving the repair further. For example, you could generate new tests. And for that, we have used a technique called fuzz testing, automatically try to generate new tests so that they can distinguish the repair more and more. And this is a technique that we call as fix to fit, but probably I will not get into a terrible amount of details on this. And we could then further make the search more and more targeted. So at this point of time, so given that we are in 10:30, so I have about 10 plus minutes or so, I'll probably move into the applications of repair. So these are three applications that we have looked into: repair of security vulnerabilities, repair of embedded software, and repair as feedback for programming education. So I'll briefly mention, to keep the talk contents broad, briefly mention these applications and would be happy to take more questions if there is interest. So the first application that we mentioned is repair of security vulnerabilities. This, I think, is a fairly immediate application. There is quite a bit of space, and if somebody is in the area, I think there is quite a bit of opportunity for them to go in and do influential work. As we know, security vulnerabilities take a long time to fix. And so this is the data from 2019. So for example, even critical vulnerabilities on an average take 50 days to fix. So if you have a template-based approach, which is further dictated or guided by more sophisticated techniques, then you can reduce the exposure to the security vulnerabilities. So this is an approach that we have tried out, and there are also other researchers who are trying out template-based approaches. In our approach, we consider templates based on the kind of the vulnerability. So for example, for a buffer overflow, of course, this would be the template. The key point is, given the template, again, we will be doing specification inferencing from a single exploit. That means we don't assume we have a lot of tests. There's only one failing test, which is the exploit, and which actually demonstrates the vulnerability. And from there, just from that one failing test, we will try to find out what is causing the vulnerability and try to curate it as a constraint. Okay, and this is actually achieved. So we generate a specification which works for all tests from one single failing test. And this is actually made possible by hooking up into the sanitizers, which help observe the vulnerability. So given this template and given the hookup to the sanitizers, we can actually generate a constraint, which is what should be preserved to rescue the program from the vulnerability. Now, once you generate that constraint, so this is really the key part. Once we generate that constraint, there are many, many techniques that are possible. The one that we do is one of calculating the weakest, what we call as the weakest precondition. So without getting too technical, we can understand it this way, that given the constraint that needs to hold, that we generate from one failing test or exploit, we try to propagate that constraint back. Okay, for this constraint to hold so that the buffer overflow does not happen at this particular location, what other constraints should hold in this earlier line of the program? What other constraints should hold in this earlier line of the program? So we try to ask these questions through a backwards constraint propagation called the weakest precondition calculation, which many of you would be familiar with. And in the process, we can also generate multi-line fixes very, very naturally, because we think now we see the repair process as one of proof obligation dispensation. So the first step was to generate the proof obligation from the one single exploit. From the one single exploit, we generate the proof obligation, and then we can dispense this proof obligation as we go backwards and dispense it at different lines in the program as well, thereby leading to multi-line fixes. So this is actually the overall. I will not go into the details of implementations and experiments, even though each of the individual works or papers might have that. So this is the overall architecture given the one single test case and the buggy program. We would first try to generate the crash-free constraint, what we call as the crash-free constraint, CFC. And then through a symbolic execution engine, we would try to do the backwards propagation, because the backwards propagation can be implicitly achieved by a forwards propagation of a slightly different property. And then we would have a backend synthesis, actually using the second order reasoning based synthesizer that I mentioned earlier for synthesizing the patch. Of course, this kind of a template-based approach, if you are in the domain of security vulnerability repair, that is a more specific domain. So you cannot expect the general purpose. We cannot expect the general purpose repair tools which work for arbitrary errors to work as well as this customized tool. So of course, the general purpose tools do not work as well, and this works much better. So we also curated a data set for this, because when we started working in this, we saw that no good data set is available. So that this problem becomes solved, because this is really a problem that can be solved, and this is of immediate need. We also curated a data set so that people can work on that and hopefully advance the field, and we can have more contributions in the area. Another application which is possible, we looked into it a little bit, but I think a lot more is possible, is in the domain of embedded software. Oftentimes when you have embedded software, we also have a reference version, which is the correct version of the software. But the embedded software is written for an embedded platform, which may be resource poor, and so on. That means maybe you need to write code which has less checks, and the code needs to be low energy, and so on. As a result of which, it may miss certain checks and introduce certain errors. So here, in this particular approach that we looked into, we can understand it through this contrived example. Suppose I have a buggy binary search, and my reference implementation is a correct linear search. So of course, the code of linear search is very, very different from the code of binary search. But I would use the correct linear search as the reference implementation for the buggy binary search, and I would try to generate fixes for the binary search. How? Well, the flow would be like this. It's really, we call it a counter example guided inductive kind of reasoning or repair. So if you're familiar with counter example guided inductive synthesis, there would be some similarities. So from the buggy program and the reference program, through a simultaneous symbolic analysis, we would generate a verification condition and then see whether it is already a suitable patch. If not, then there would be a counter example, and this counter example would give Angelix values, which we can then use for the purpose of the synthesize another patch, and go on in this loop. So what we found out is that, and again, these are initial, this domain, again, a lot more exploration may be needed. When we look into the Linux Busybox, which is sort of one of the popular implementations of Linux for embedded devices, and try to use GNU core utils as reference, and vice versa, that this kind of a reference-based approach produces less overfitting repairs. Again, this is expected because the reference is a much richer source of specification than the test cases as compared to the test-based repairs. Okay, the application, I think I don't have a whole lot of time. The application I will end with is this education. So we have also used automated program repair for intelligent tutoring, in particular automated grading and hint generation. In the interest of time, I'll not go into the details of the technique, but just leave you with this particular slide maybe, where we can see the repair in progress on a Python program, which is supposed to do this task. So we have an incorrect student program and a reference solution. So the reference solution may not even have the same control flow as the incorrect student program. So one way of generating interesting feedback for the student might be to first refactor this, produce a correct solution which actually meets the control flow. And once the control flow is the same, then you can align the two programs, and then you can do the block repair based on the repair of expressions, the technology that we mentioned earlier, like this Angelix and so on, where we repair individual expressions. And then exactly you would generate this feedback that this less than should be less than equal to, this else, this is wrong, this should just be pass, or that means nothing, and this whatever is being returned is wrong. So this is one approach we are examining, both for auto grading. For automated grading, we did a fairly significant amount of user study some years back in IIT Kanpur in India with our collaborator Amay Karkare. And subsequently, we are also looking into the application of these technologies in NUS, but that is work in progress. I would like to acknowledge the National Cybersecurity Research Program from NRF and end with this slide. If you are interested in this area, if this talk has generated a little bit of interest in the area, I would request you to look up this article, which provides a review or an overview of this area. And this is really a diagram which is sort of showing the various approaches. With that, I would like to thank again the organizers for kindly inviting me, and would be open for questions.
If you can hear me, that's me clapping. Thanks for the interesting talk, as always. Do we have any questions? If you would like to ask yourself, kindly unmute yourself and then speak. Otherwise, you're welcome to send the questions in the Slack or the chat so I can relay the questions. While we are waiting, maybe I can start with some questions that we already have. So the first question is from Malay. So he's basically asking, well, there are different languages. Different languages typically have different kind of errors. One example would be Rust. They're putting a lot of effort to get rid of many of these memory safety kind of issues. So the question is really whether there are differences in terms of repairing different languages.
There would always be. That's indeed a very, very valid question. There would always be differences based on the languages, people would have a specific kind of coding styles, and more than that, also different kinds of error patterns. So error patterns always creep in, and having that as an input to your repair process is always advantageous. One of the difficulties one may face in moving from one language to another is to retarget the analysis. This is certainly a valid point. One possibility is to work on intermediate representations. That means to target the analysis on intermediate representations. So I think my answer would be twofold. One is that it is always useful to look into the error models of the different languages and factor that in rather than having a purely analysis-based approach. That could be an interesting input to the analysis. And retargeting the analysis, as we found out, is always some amount of work. And for this purpose, also looking into other alternatives like intermediate representations is also generally useful.
Right. We have another question from Ling Ying. So the question is asking about neural networks. Now, neural networks can be considered as a special set of programs. They share some similarities to traditional programs, but also some differences, I guess. And then the question is, if any of these techniques or methods that you talked about could be potentially extended to repair neural networks.
That's indeed an excellent question and a very topical one for sure. So I think it's certainly possible, but the repair would look very different. The repair would be more along the lines of adjusting the weights and so on for the purpose of the neural networks. And also for this kind of, it also is a matter of what property we are repairing for the neural networks. So this is something we are investigating, so I would not have a full answer. But such fine-grained properties, like in a program, we have a very clear definition of test, and the test has an expected output, and then if it doesn't meet, it's a failing test. This is a very, very fine-grained property. So whether we will be looking at such fine-grained properties and repair of those fine-grained properties for neural networks, or we look into repair of hyper properties for neural networks. So which might be of quite a bit of interest, like properties like fairness, privacy, and so on. For that, certainly these kind of approaches can be retargeted. That we have looked into. The fine-grained properties, the repair of fine-grained properties, even though that is possible, we did not look into it yet. Yeah.
I see. Well, that makes a lot of sense. Actually, we are looking into that a little bit as well. So, yep. One student is asking whether you can clarify a little bit on this error model of different programming languages.
Yeah, for example, depending on the nature of the features in the programming language, you might make more errors of a certain kind. For example, in C, there is hardly a student who hasn't made very pernicious errors with pointers. So it depends on what the programming language is and what kind of errors people are prone to make. In fact, for the application of repair in education, some of the early works looked into providing explicit error models exactly for this reason, because that's a domain where the error model is even more important. It is not just the programming language, but also what kind of, for that particular university, what kind of errors do students usually make, or for this particular assignment, what kind of errors do students usually make. So in those kind of setups of the repair problem, the error model becomes more important. And it's important to realize that, for example, the education application is a harder problem sometimes than the automated program repair problem in general. This sounds counterintuitive, but it's not hard to see, because most of the times when we are repairing a program written by a professional developer, it is almost correct. So the search space of fixes is actually relatively small, because there is this competent programmer hypothesis. On the other hand, when we are looking at a programming assignment written by a first-year student, it might be greatly incorrect. So even though the program is very small, the scalability is not in terms of the program size, but in terms of the search space. So therefore, repairing it might be quite difficult, because the student might have made terrible errors. So for those purposes, having an error model to guide the repair sometimes can be quite useful. For
Well,
those
that makes
setup.
perfect sense. Yep. I mean, what I'm thinking is, this is from me. If the program is completely wrong, then it's basically generating a new program from scratch, and then that's obviously hopeless.
That's right. So that's the automated programming problem. The repair problem. That's a great question, because of course, if through learning we could generate the program completely automatically, that would be quite nice, right? But we are not there yet. So this is a matter of perspective, whether we are moving to automated programming completely. So some of us believe that maybe we are moving to automated programming completely, or maybe we are not there yet. One possibility, and it is just a possibility that may emerge, is that we still have learning, for example, deep learning, to do co-opt certain components in our software system. But the inaccuracies of the deep learning, they are compensated for by some amount of program repair in the remaining conventional software system, which is communicating with the learning components. So even today in a self-driving car, it's not that all of the software is deep learning, right? It only certain components are deep learning. So the inaccuracy or the unreliability, whatever you call it, the untrustworthiness of those components, can it be compensated by repair in the rest of the software? This would be a very grand, it would be very nice if some of the research groups here today would take up a vision like this, would take up a direction like this. Yeah. There's another question, it seems. Yeah.
Well, yep. So one student is asking basically, you mentioned a lot of this overfitting, which is a term that I, yeah, quite like how you describe the problem. So in general, I think this problem is basically due to the lack of a specification, and
Yes.
then we have to basically have these, pretty weak specification, and then that runs the risk of overfitting. And then in general, I guess the problem is still how do I get this, strong enough specification so that my fix will work, you know. And then towards that end, maybe I can well twist the question a little bit. Is there any study in terms of like if I'm repairing according to test cases or I'm
Yeah.
repairing to according to user assertions, then what like how many test cases would be sufficient, or what kind of assertions that will give me certain confidence that I should be able to repair certain kind of bugs?
Yeah, the confidence would always be based on the usual things in testing, like coverage and so on. So of course, if you could have path coverage, then that would be very nice and so on. But in general, you may not always have tests covering every little corner case, or even if you did, that does not necessarily mean, even if you have a test with 100% coverage, that does not mean that there aren't other corner cases. Even if you have 100% path coverage, doesn't mean that there could not be a violation of the assertion. So all of these things we know. So the goal really is to improve the specification inference more and more and more and more. So you have a very weak specification, you have a very weak exam, everybody can pass the exam. So how do you kind of make it like a higher bar so that not all patch candidates can pass? If you have a very critical piece of software, so these are some of the applications we are looking into. If you have a very critical piece of software, usually having a reference program helps. That gives you a certain amount of confidence. This kind of a simultaneous analysis, or whatever you call it, gives you a certain amount of confidence that, okay, the repair will work for all possible test cases. The security vulnerability work that I mentioned, that one actually works for all test cases. That means from one single exploit, you try to generate a general constraint, which is supposed to be a property that is supposed to be preserved by all test cases. And then since the constraint propagation and all of these things are quote unquote provably correct, assuming there are no bugs in the symbolic execution engine and so on. So therefore you can be assured about the veracity of the fixes. So that makes sense for security vulnerability, where the errors are very shallow, but you need absolute assurance that it has been fixed.
Yep. All right, yeah, so I do have a few questions here, but we are running out of time. Maybe we can do this offline later somehow.